So I'm going to be going over the solution to ARMYOFME in this video from January Challenge 2020. So observation 1, and this statement comes from the problem statement. So it says the strength of a group of clones is the maximum number of clones in that group such that their positions in the line are consecutive, and they can be reordered in such a way that their IDs P of I also become consecutive. So it says that the positions in the line are consecutive, so that means that you want to choose a consecutive subarray, let's say from L to R. And it also has a condition that they can be reordered in such a way that their IDs P of I also become consecutive. And this condition actually becomes maximum of the subarray minus the minimum of the subarray plus 1 is equal to R minus L plus 1, or the number of elements in the subarray. And this is true because each value from the minimum of the subarray to the maximum of the subarray should appear so that they can be reordered in a way so that their IDs become consecutive. So there should be max minus min plus 1 elements. And we know that the subarray has R minus L plus 1 elements. So that's why that's why for good subarrays, these two need to be equal. Also for bad subarrays, max minus min plus 1 will be greater than the number of elements. So here in this example, we have this array P. And for the subarray from 1 to 3, for P of 1 to 3, we have the subarray 1, 3, and 2. And you can use this condition to check if it is a good subarray or a bad subarray. So maximum, which is 3, minus minimum, which is 1, plus 1, that's equal to 3. We can also calculate R minus L plus 1, and in this case it's 3. And 3 is equal to 3, which means that the subarray is good. Let's check if the subarray from 0 to 3 is good or not. So we use the same process. The maximum of the subarray, which is 5, minus the minimum of the subarray, which is 1, plus 1 is equal to 5. And the length of the subarray is 4. 5 is greater than 4, so we find that the subarray is bad. So first, let's assume that the queries can be processed offline, and we will process them in increasing order of R, similar to how we solved the standard problem queries for a number of distinct elements in the subarray. So if you don't know what this is, I've included a link to a Geeks for Geeks article talking about it. So I'm going to start writing some pseudocode. So we will have an array answer such that the answer of L stores the maximum length of a good subarray that starts at L. Initially, answer is just an array of n zeros. And we will iterate for R from 0 to n minus 1. In the first step of the iteration, we will update the answer array for R. To do this, we will loop through all subarrays which end at R. And then we use our formula in observation 1 to check if the subarray is good. And if it is, we update answer of L with the length of the subarray. Lastly, we answer queries which end at R by taking the maximum of the answer array in the range from L to R. Unfortunately, this works in quadratic time, which is too slow for this problem. And we can slowly optimize the solution to O of n log n time with a segment tree. So here you have our code, and let's use a new array b, and it's of length n. So at the start of each iteration, we will update b so that b of l is equal to the maximum of a of l to r minus the minimum of a of l to r plus l. Now to check if a subarray L of R is good, we can simply check if B of L is equal to R. Because if B of L is equal to R, then by the formula we used before, you would find that it's equal to 0. So now in each iteration, we have 3 steps. Step 1 is to update B so that B of L is equal to the maximum of the subarray minus the minimum of the subarray plus L. And step 2 is to update the ANS array for R. And step 3 is to answer the queries. So let's look at step 1. And this entire formula might look complicated at first. So let's simplify this problem so that we only have to maintain the array B such that B of L is equal to the maximum of the array A from in the range L to R. So we will use the stack algorithm for finding the next greater element for each element in the array. And if you don't know what that is, I have included another article in the description. So here's what the stack algorithm looks like. So you also iterate for R from 0 to n-1. And while the stack is now empty and the top of the stack is smaller than our current element, we pop the element off of the stack. And at the end of each iteration, we push R on top of the stack. So let's assume that we have an array P which looks like this. Also, we have already ended the iteration R equals to 6. Right, and after the iteration, our array B looks like this, and the stack looks like this. For example, the B of 0 is 8 because the maximum of P from 0 to 6 is 8. And then also B of 4 is 5 because the maximum of P in the range from 4 to 6 is 5. And then the elements in the stack correspond to indexes in the array. So for example, 6 corresponds to this element in the array, which has index 6. So during iteration R equals to 7, what do we do? So first we need to add A of R to the end of B. So we look at A of R, which is 6. So then we add 6 to the end of B. So now array B looks like this. And then look at the top of the stack, which is 6. And we find that A of 6, which is equal to 4, is smaller than A of R, which is equal to 6. So this means that we need to pop 6 off the stack. And after you do that, you look at the range of elements such that the range of elements in B which are equal to A of 6, which is 4, and it corresponds to this range. And we need to add A of R minus A of 6 to this range. this is equal to plus 2. So we add 2 to both of these elements so that the subarray, this range of elements becomes 6. And then we repeat the process again. So now the top of the stack is 4. So we compare A of 4 and A of R. And A of 4 is 5. And A of R is 6. And 5 is smaller than 6, so we should pop 4 off of the stack. Now we find the range of elements that are equal to A of 4, which is this range. And then we add A of R minus A of 4 to this range. And this is equal to plus 1. So when you add 1 to all 3 elements, they become 6. And then we repeat this process again. The top of the stack is now 1. So we compare A of 1 with A of R. And A of 1 is 8, which is greater than A of R, which is 6. So we stop this process. And then after we stop the loop, we should push R onto the stack. So in this case, we need to put 7 onto the stack. So now at the end of this iteration, you have updated B so that B of L is equal to the maximum of A from L to R. So for example, this is B of 0, and it is equal to the maximum of A of 0 to 7. And as another example, B of 5, this is B of 5, and it is equal to the maximum of A of 5 to 7. You can check that it's true here. So the elements from 5 to 7, the maximum is 6. So now I'm going to start writing some pseudocode for the modified stack algorithm. So the first step is to set B of R equal to R. And then we need to find the range to update. So the right boundary will be the top of the stack. And then the left boundary will be the top of the stack after we pop the top element of the stack plus 1. And if the stack is already empty, then we assume the top of the stack is -1. So if the stack is empty, then range L will be equal to 0. And then we also need the old value of this range, which we find as A of whatever the top of the stack is. And then we update the range, so we add the value of A of R minus old value to this range in array B. And using a segment tree, we can update array B in O of n log n time total with add B updates. So we know that this works for B of L if we need to maintain B of L equals to maximum of A of L to R. But what about B of L equals the maximum minus minimum plus L? And then we can simply copy the stack algorithm, but for the next smaller element as well. so that we can maintain the minimum inside of B. And also at first, we need to set B, we need to set B of I equals to I for all I from 0 to n minus 1. So step 2 is to update the ANS array for the current R. So originally we had this loop here as shown to update the ANS array. We know from observation 1 that B of L is greater than or equal to R, and we also know that B of R is equal to R. And note that if L is greater than R, then B of L is greater than R. So in fact, we can remove the restriction that L is smaller than R, is smaller than or equal to R, and simply loop for L from 0 to n minus 1. We can rephrase our update as for all L, take the max answer of L with x minus L if B of L is minimum. And in our specific case, x is R plus 1. And we will call this a max ANS update with value R plus 1. And it turns out that we can support max ANS updates along with add B updates with a segment tree in O of n log n time. So now step 3 is to answer the queries. So for each query, LR such that R is the end of the query is R in our current iteration, we should output the maximum of the ANS array from L to R. And this is relatively simple to do. We can store the ANS array in the segment tree, and then you can perform range maximum queries on the segment tree to do this part in O of n log n time. So what is this segment tree that we're going to use, and how exactly does it work? So let's review the operations that we need to support. We need to support add B updates with value x, which means that we add x to the range L to R of array B. We also need to support max ANS updates with value x, which means that for each L such that B of L is minimum, we set the answer of L to the maximum of the old answer of L with x minus L. And then we need to support the queries. So basically just return the maximum of the ANS array from L to R. And here I'll introduce some helper functions in our segment tree. So the first helper function is the apply function. So in this function, we basically apply updates onto node I. So we apply an add B update with value x1 on node I, and you also apply a max ANS update with value x2 on node I. We also need the function pushI, which pushes the lazy updates to the children of node I. And we also have combine_I, which takes the information from the children of node I to calculate the information for node I. Also, in each node, we need to store some information. So the first thing we need to store is min B1, which is the minimum value of B in this node. And next, we also need max b2, which stores the maximum value of negative L in this node such that b of L is minimum within this node. And we also need max ans, which is the maximum value of answer in this node. And we need information to store the lazy updates. So lazy at b is the lazy value for at b updates. Similarly, we have lazy max ans, which is the lazy value for max ans updates. So what happens in the function apply? So first, min b1 stores the minimum value of b in this node. So we should increase it by x1. Next, we also, since we need to propagate the add b update to the children, we should add x1 to the lazy value of this node. You also need to apply the max ans update. So in order to do that, we'll set max ans of this node to the maximum of the old max ans of this node, and x2 plus max b2 of this node. So basically, we choose max b2 of I because max b2 stores the maximum value of negative L in this node such that b of L is minimum. And lastly, we also need to apply this update to the children. So we set the lazy max ans of I to the maximum of x2 and the old value of lazy max ans of I. So now we need the push function. So in push, we push the lazy updates to the children of I. And you might, so basically we apply the lazy update to the left child, we apply it to the right child, and then we remove the lazy update since we have already applied it. So it looks straightforward, but actually this is wrong because we should only apply the lazy max ans to the children with the minimum value of b, since we only want to apply this update to all L such that b of L is minimum. So if the minimum of the value of b for the left child is not equal to the minimum value of b for the entire node, then we should not apply our lazy max ans to the left child. And the similar thing is true for the right child. So to correct this, we should check that the child we are applying the update to has the minimum value of b. So for example, this is the minimum value of b in the left child after we apply the update. So if it is smaller than or equal to the minimum value of b of I, then we should push the max ans update. Otherwise, we should just give it 0. And the same thing happens for the right child as well. In our combine function, we need to combine the information for the two child nodes of I. More specifically, we need to calculate min b1, max b2, and max ans from node i's children. So first, for min b1 and max b2, we should check which child has the smaller value of b. So if the min value of b from the left child is smaller than or equal to the minimum value of b from the right child, then we set min b1 and max b2 to its values from the left child. Otherwise, we take the values from the right child. And note that if the minimum in the left child is the same as the minimum in the right child, then we still use the left child because the left child will have the greater value of max b2. Lastly, we need to calculate the max answer for this node, and we simply set it to the maximum as the max answer from the left child and the max answer of the right child. So using the segment tree, we can perform all of the 3 steps that I described earlier efficiently. So let's recap the offline solution. So we start with, in our segment tree, we start with ans equals to all zeros and b, and all b of I equal to I. And then we iterate for r from 0 to n minus 1. And in step 1, we use our stack algorithm along with the range add b updates to maintain the values of b. In step 2, we apply the max ans update to the entire segment tree. So now our ans array is properly updated. And finally, in step 3, we take each query that ends with index r, and then we perform a segment tree range max query to find the answer. And remember that the problem wants online queries. And to do this, we can simply, instead of using a normal segment tree, we will use a persistent segment tree. And I have also included a link for that in the description. And if you need more specific implementation details for my solution, refer to my commented code in the description.